Hello guys. So today is the day 2 of learning the deep learning playlist. So today is the very important day. Basically today we are going to start the deep learning playlist. Already started basically, and today I will explain you the optimizers and activation function, like how they will work. If you know this, like optimizers and activation function, then you know 80% like how ANN CNN will work. Like in every deep learning neural network these functions are used, so you have to know all of this. So let's start the playlist, and I think you are there with me. Let's start, guys. Take some energy and let's start our deep learning playlist. So basically we have covered the ANN part, like how ANN works. So ANN, CNN, RNN is the all of these are the part of deep learning, and why deep learning is becoming popular because of the rise of data, big data basically. The data size will increase, the performance of also the deep learning models is also increasing. And these are the some examples where deep learning is used. Basically in every field nowadays deep learning is used. And this inside the ANN, or we can say a perceptron, input layer is there, hidden layer is there, weights and activation function, optimizers and losses are there. And this is the guy Jeffrey Hinton which have designed the deep neural network and discovered like this is. And we have discussed about like due to chain rule of differentiation the model will be very if the model will be very deep, then your bits of the initial level will not be learning as they we want to learn. So we have to use a good activation function. The problem will be occurred in RNN because any function you can use, there is no any skip connection, so the problem will be occurred in RNN. So to reduce this overcome, like if we use a sigmoid activation function, this problem will occur. So the scientists have discovered a second neural network, or we can say optimizers, not optimizer, we can say activation function, basically to activate the neuron. Like which activation function we have to use. So if we use a sigmoid activation function, in the previous lecture we have seen if we use a sigmoid activation function, due to its value ranges from 0 to 1, the derivation of this will be ranges from 0 to 0.25. So due to this, the derivation will be every time coming lesser and lesser, so this neurons will not be learning as we want. So to reduce this problem, like vanishing gradient, the problem we know that this problem called vanishing gradient problem. So to overcome this problem, the scientist has discovered the new activation functions. These activation functions are 10H, ReLU, pre-ReLU, or leaky ReLU, or Swiss, and Adam. No, Adam is the optimizers basically. ReLU is the activation function that we have to use. So now learn the sigmoid activation function firstly. So we have already discussed like this function value ranges from minus not 0 to 1. So if we apply a derivation on this function, this value ranges from 0 to 0.25. So if we train a deep neural network, the vanishing gradient problem will be occurred due to the bits of the initial layer will not be learned as we want because of vanishing gradient problem, because of we can say a chain rule of differentiation. So this will be not learning, like this will be bit will be very small and small every time. For binary classification is like, now we are seeing the advantages and disadvantages of this sigmoid function. So clear prediction, very easy, like 1 or 0, this will predict. Binary classification suitable. If you are doing binary classification, then you can apply this activation function, like this activation function, this sigmoid. Prone to, like these are some disadvantages. We have already seen that, like prone to vanishing gradient problem. Function output is not zero centered. Yeah, so this is also a problem. This is not zero centered. Efficient bit updation. Like, and what happens if we have a zero centered curve, then the bit updation will be effective. So that's why this is not a zero centered, because this from ranges from 0 to 1. So this problem is also occurred. Mathematical operation are relationally time consuming. Yeah, because the formula is to calculate the activation function is 1 upon 1 plus e raised to the power of minus z, because it's calculating the exponential function e raised to the power minus. That's why it will take some time. So these are some disadvantages. So that's why we don't have to use this activation function inside our application or a model basically. Zero centered, it's really standardization, effective bit updation. If you want a good optimize activation function, then it should be a zero centered. So this is not a zero centered, that's why we don't have to use. Basically, we have to use this function at the output layer. If you have a binary class classification, then we have applied this activation at the output layer, because we want output in a 0 or 1. That's why. Or if you are doing a multi-class, then apply a softmax activation function. Basically, softmax, the formula is e raised to the power of z upon summation of e raised to the power of z. Basically, z, or we can say that I is basically output of the every layer. And now coming to 10h activation function. 10h. The formula of 10h is e raised to the power of minus z minus e raised to the power of minus z upon e raised to the power of z plus e raised to the power of minus z, basically. Or you can say z replaced with x. So the zero centered problem will be gone in this. Like this formula is zero center. Like this value ranges from minus 1 to 1 in 10h. And this for like values ranges from 0 to 1 of the derivative values. So this in sigmoid basically ranges from 0 to 0.25, but this in 10h ranges from 0 to 1. So like this. So in this also the problem is vanishing gradient occur. If you will create a deep neural network, it is good than like sigmoid, but it still it have a vanishing gradient problem, because its value ranges from derivative value ranges from 0 to 1. So again, if you apply a very long derivation like chain rule of differentiation, then again the problem will be remains. But it is zero centered, so bit updation is effective in this like 10h. But the disadvantage is also prone to vanishing gradient problem, and the second most important disadvantage is time complexity. Now you have to calculate e raised to the power of x and e raised to the power of minus x also. So it will have many, like it will take huge time to calculate. So it will have this problem still. Now coming to ReLU activation function. This is the third type of activation function is ReLU, rectifier linear unit, also known as. So now this is also a zero centered because it's passing from zero. And the formula is ReLU is basically max of 0 comma x, so it will looks like this and this. And if you apply a derivation on the ReLU activation function, the it will be shown like x, and if you do a derivation of x, x is equal to 1, so it will be 0 and 1, 0 or 1 basically. So if the value is greater than 0, it will be 1, and so this is now. So what happened in this dead neuron problem will be occurred, like it is giving 0 or 1, so the bit will be sometimes 0 or maybe 1 only. So this is also a problem, like bit, if ReLU output is 1, then bit updation will happen, and if the ReLU output is 0, dead neurons directly. So W new equal to W minus derivation of loss function with respect to old equal to 0, because the ReLU output is 0, or we can say activation function is giving 0, then the output will be 0. So now the bit will be not updating if 0. So dead neuron. Basically this problem W new equal to W called dead neuron problem. So if Z is positive, then it is 1, and negative, then it is 0. So now coming to the advantages and disadvantages of ReLU. So solving Banaching gradient problem. It will be able to solve Banaching gradient problem because now the bit will be update or not update only. It will not like 0 0.0 something like that. Max of 0, so calculate the formula is max of 0 comma x. So the you see the calculation is very fast, because here you don't even a calculation, only max of 0 comma x. If it is less than 0, then it is 0, and greater than 0, it will be that number only. So the calculation is very fast. So this is the advantages. It is much faster than sigmoid or 10H. The disadvantage, dead neuron, we have already seen that, like this is the biggest problem in the dead neuron, because if the activation function output is less than 0, then it is directly say that it's a dead neuron. The ReLU function output is basically 0 or positive, so it is not 0 centered basically. The ReLU function is not centered because it is 0 or positive number. Basically it's a 0, max of 0 or x basically. So now coming to the third one, it's leaky ReLU and permanentric ReLU, or also known as pre-ReLU we can say. Now see that the formula is same as ReLU and LU, but some difference, like 0.01 into x comma x max of this one. So which is now it's coming like this from negative to 0. It is not exact 0, it is touching like 0.001, like something like that. So it will now able to solve dead neuron problem, which will be held in ReLU. So now this problem is also solved in leaky ReLU. Basically alpha is basically very small number, 0.01. You can take it any number, it's a basically a hyperparameter. Advantages: leaky ReLU has all advantages of ReLU. It removes the dead neuron problem. It is not geocentric. Again, like advantages all there in ReLU, like the calculation is very fast, and it is also able to solve dead neuron problem, and the like Bayesian gradient problem is also solved. This is the biggest, like we can say, advantages, and this we can use in our in a model to build a model as a activation function. Most of the like 90 to 95% or 99% In between we can use ReLU or leaky ReLU as a activation function because it's give good accuracy as compared to any other activation function. But disadvantage, it is not zero centric, so the weight updation will be not effective, but it is good. Now coming to the fifth one is exponential linear unit or ELU or Swiss. Swiss is there or not? Swiss is not there. Okay, so now learn this only. Liquid ELU done. ELU exponential linear unit. So the formula will looks like x if x is greater than 0, otherwise means simply less than 0, then alpha into e raised to the power of x minus 1. So it is now looks like this. Shui, shui. So the if the value of x is greater than 0, then it is same as ReLU and leaky ReLU, but if it is less than 0, then it is different. Like in ReLU it will be 0 simply, leaky ReLU it's 0.001x, and in ELU exponential linear unit is alpha. Alpha is basically a hyperparameter into e raised to the power x minus 1. So now if you do derivation, then it will looks like this, shim, 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 and 1 if x value is greater than 0. So now advantage, note that ReLU issue, like it's same as we can say a leaky ReLU. All advantages as ReLU, zero centered. This will be a zero centered, you can see that. And a disadvantage, slightly more computationally ineffective. Yeah, because here we are doing a exponential function, so it will take some time, like time complexity it have, like this is but it have all of the, it will solve all of these problem like vanishing gradient problem, time complexity is there, but it solve no dead neurons or dead neuron problem, and zero centered is also there to solve ReLU problem. It is used to solve ReLU problem. We can use this function, but it will take some time, so that's why like 90% or 99% we will use a ReLU activation function only. Now coming to softmax activation function, this is used for multi-class classification problem basically. If you want a output like of multi-class like cat, dog, monkey, horse, then we will use a softmax activation function. If we have a binary class classification like 0 or 1 only, or two classes, then we use a sigmoid activation function. The sigmoid activation function is 1 upon 1 plus e raised to the power, but in softmax this will be e raised to the power of by I upon summation of e raised to the power of by I. We can see that summation. So this is for softmax, and for cat e raised to the power of minus 1 we can say 0.035. This is the probability. You see, it will give probability of the cat, dog, monkey, and horse. Like which function, which activation function to use when. This now we will learn. Remember this words now. I am saying something now. Listen very carefully. If you remember this thing, you will remember everything that I have taught you about activation function. Now, so if you have a output of two classes, then apply binary classification, or we can say a sigmoid activation function in the output layer, and ReLU activation function in between. Like yes, see that we can use ReLU or its variant like PReLU, leaky ReLU, or ELU, but use ReLU. I say that directly use ReLU because it will take less time complexity, and it also like overcome the vanishing gradient problem, but it has a dead neuron problem and zero centric, but you can use it, it will give a good accuracy. Now if you have a multi-class classification output like cat, dog, something like that, then use a softmax in the output layer, and in between you can use this function like relu and its variant. So that's how we will solve. And if you have a output like cut regression, then use a linear activation function in the output layer basically. Now coming to the loss function and cost function. This is done. I think you are able to understand it. Now loss function and cost function we will learn. These are some. So today we will learn about this 23rd PPT page, and after that like 24th we will cover in the next lecture. So now we have to learn about this loss and cost function. So what is cost function and loss function? So basically cost function when you are finding a error for one data point. Suppose you have 100 data point to train your model. So if you want to calculate a error of 1 point only, then it will say as a cost function. But if you take a summation of all this cost, like of this point, this point, this point, then this will known as loss function basically. So cost function or loss function, no, it is written in a wrong way. MSC. It is known as cost function and it is known as loss function basically. Cost is for one data point and loss is for all the summations. This is written in a wrong, I think. Loss, cost function. Loss and cost function. Wait, I will check it. I don't have internet now. Wait, I will check in my mobile. Wait 1 minute, guys. I have some confusion related to cost and loss function. I will confirm it and let me continue after this. So the loss function is to capture the difference between the actual and predicted value for a single record base. Cost function aggregates the difference of the entire training data. Okay. So the loss function loss and the cost is for aggregation. Yeah, cost is for aggregation. Okay. I have some confusion. It is written in the right way. Okay. Sorry guys. So loss function. Loss basically is for one data point and cost is for summation of all the data points. Error basically we can say that. So this is the bias and so now if somebody say what is the difference between loss and cost function. So loss is basically for one data point. Basically what is your loss basically? So we can say I have a suppose think like in a stock market. I will say what is your loss. So you say a loss for 1 day only. If I will ask you about what is your cost function, what is your cost function, then you will tell summation of all your losses from the previous, basically previous stock market. So this is the difference. Now we will have to remember this word like cost and loss function. So loss is for 1 day, or we can say one data point, and cost is the summation of all the losses. Okay, optimizers basically. Now we have some optimizers, and the first one optimizers is known as gradient descent. I think everybody knows about this gradient descent. So we will learn like different types of gradient descent in the next lecture. So now in ANN, for classification, we have errors like hinge loss and some log loss is there. For regression, we have mean squared error, mean absolute error, Hubble loss, hinge loss, RMSE, and for classification, we have a log loss. I think. So mean, now learn mean squared error. Basically, mean squared error means basically we have to take a mean of that error. Mean means we have to take the summation. Summation of I equal to 1 to n by minus by predicted का whole square. By is the basic actual minus predicted का whole square and take the average of these values. So this is the global minima in the gradient descent, and this is the bit updation. Like now gradient descent looks like this because this is a quadratic equation for a loss function, or we can say a cost function have a quadratic equation. So this will looks like a quadratic equation of the gradient descent. Basically the formula of gradient descent is basically w equal to w world minus summation neta, we can say, into differentiation of loss with respect to w world. So this will gives basically a slope of that function. This is the global minima, and there are many locals minima. Basically if you are using a binary classification, then this will stuck in local minima. So this is the gradient descent formula that we have to apply. Now coming to advantages and disadvantages of MSE. MSE is differentiable, like mean absolute. This is the formula of MSE, mean absolute mean squared error. So it is differentiable. So this is the advantage. It has one local or global minima. It converge faster. Disadvantage: not robust to outlier. Penalize the error. Basically, we know that the quadratic equation is there, so it is differentiable. It has only one local or global minima. Basically, it converges faster. These are the advantages. Now coming to disadvantage. Disadvantage is that not robust to outlier. Like how this can be not robust to outlier. Suppose we have a linear regression line. If one basically outlier will come, then the line will be shifted toward this. So due to this outlier, the line will be shifted. So because this point will give some error according to this line. So to reduce this, basically what we say, this error, to penalize this error, our model will be shifted toward this. But like this gradient descent formula will be shifted according to this. So now our model will not work good because of this outlier. So this is the problem in gradient descent basically. So because gradient descent depends on this mean squared error formula, so this will not work good in case of outliers. Now coming to mean absolute error. So the mean absolute formula is for loss. For basically we can say a loss is by minus by head mode, and for cost function is take the summation of this. So now this will looks like this and this. So now it is somewhat advantageous. It's robust to outlier. How? because here we are not squaring our out like error. Here we are taking only the mode, so that's why it is still somewhat tilted toward the outlier, but not as much, because here we are not doing the square of that error. And the disadvantage, convergence usually takes time in mean absolute error. Convergence means basically if you apply this error in your activation function of a gradient descent, then convergence usually takes some time because of this basically sub quadrant. Basically it's not a quadratic equation, that's why. Now coming to MSE, or we can say a Huber loss. Huber loss is basically, the formula is something like that: 1 by n summation of I equal to n by minus by k square if by minus by predicted is less than equal to delta. Delta is basically a hyperparameter. This will be basically we can fix it, or that at the time of training model will we fix it. No outlier. And the formula, if it otherwise, it's delta into by minus by predicted minus 1 by 2 delta square. This is the Huber loss basically. So this will work fine. This is MSE mean squared error if the by minus by predicted less than equal to delta. Otherwise it is MA mean absolute error. MSE MAE mean absolute error basically is by minus by hat minus 1 by 2 delta square. If delta we can take it as a 2, or we can take it as a suppose 3 minus 3 is 9. It will comes like something like that, but it is MAE mean absolute error. If it is less than, otherwise it is this one. So it is a combination of both, no outlier. Now RMSE, root mean squared error. The formula will be like this: root mean squared error. MSE we have to take a root basically. Advantages and disadvantages. So in this basically advantages is there key, what we can say, it will not take some times basically. It is square and under root is also there, so our function will not impacted by outliers, like we can say. In this MSE is there, in MSE basically penalize the output if there is an outlier, but in this no effect. It is also a differentiable, it has also a one, only one global minima is there. These are some advantage, and disadvantages, it will have to take, we have to do some calculations, like it will take some time complexity problem is there. Now coming to loss or cost function for classification problem. So now we are doing suppose a classification like binary or multi-class, then we have a like error like cross entropy, binary cross entropy, categorical cross entropy, and sparse categorical cross entropy. So now learn like what is binary cross entropy. So binary cross entropy formula is minus by log by minus 1 minus by log 1 minus by, we can say. So this formula is something like this for loss, and for we know that for a cost it will be a summation of all these values. So by actual value and by bar is basically predicted. So the formula will looks like minus by into log by minus 1 minus by into log 1 minus by basically. Sigmoid activation function. Sigmoid activation function it looks like 1 upon 1 plus e raised to the power of minus z. We already know this sigmoid activation function. So this is the formula for loss, or we can say that a binary cross entropy. Now learn categorical cross entropy. Categorical cross entropy formula looks like summation of minus summation of by ij into ln min by ij basically. Same as basically binary cross entropy, but here basically for multi-class classification categorical cross entropy it's basically we are taking summation only for all these classes. Y equal to 1 if the element is in the class, 0 otherwise. Same as this one. For binary cross entropy and categorical, and what is sparse. So basically in sparse categorical cross entropy, we will sparse our matrix. Sparse means create different sparse matrix basically. Sparse categorical cross entropy. So zeroth, first and second categories are there. So we will give some probability to this zero class, first class and second class. And the summation of all these values is equal to 1. Disadvantage. Losing into about the probability of other categories. Second index output basically. So zeroth, first, second, third, fourth, 0.2, first index category output. You see, we will take highest output out of all these sparse category cross entropy basically. This is your output, and losing these are some disadvantage like for sparse losing into info about the probability of other categories. Okay, so if this will gives a probability something like that, then we will take highest probability, and this probability we will neglect it basically. So this in the sparse category cross entropy. So where we have to apply this like, so if your data has a binary classification, then apply a sigmoid activation function and apply binary cross entropy as a loss function. But if your data have a multi-class classification, then there is two types of losses is there, like categorical cross entropy or sparse categorical cross entropy. So if your data have a categorical cross entropy and sparse matrix, basically sparse will create a sparse matrix. So if your data will have a output like 0 1 2 3 4 5 something like that, if you have a output class and which will contain outputs like, if you have a 10 class and this will gives in which location you have, like in sixth location you have 1 and other all are 0, then apply a categorical cross entropy. But if you have output like 1 2 3 4 5 6 7 8 9 10, then apply sparse categorical cross entropy as a loss matrix. So this will automatically convert your data into a sparse matrix and then apply a loss function on top of that. So that's it for sparse categorical cross entropy. Losing info about the probability of others. That's it. The right combination of activation function. Hidden layer directly apply ReLU or its variant like ReLU, clicky ReLU, you can apply it. But for output layer, sigmoid, softmax or linear, when we have to apply. So if you have a binary classification, then apply a sigmoid activation function. If you have a multi-class classification problem, then apply a softmax. If you have a regression problem, then apply a linear regression. Now, if you have binary classification problem, then which loss function to binary cross entropy we have to use. If you have multi-class classification output, then we have to use categorical cross entropy or sparse categorical cross entropy. And for this regression, we have to apply MSE, MAE, Huber loss, Hinge loss, RMSE. We can apply it. Now comes in a mind like what is the difference between categorical and sparse categorical cross entropy. So I don't have internet now, but otherwise I will show you like how. So basically in categorical class entropy, if your output class will contain it's depend on you like how you want to show your data at the time of training. So to train a model, basically you have to firstly create this input vectors like how this will be input of this your model. Like this is the input and this is the output looks like how. So if your output vector will look like you have given us number like 6 for cat, and for 6 you have created a sparse matrix like 0 0 0, and 6th position you have given a 1. Then apply a categorical class entropy. But suppose if you have directly applied a activation like you if you suppose you have created a input and output, and at the time of output you have given a number to this like 1 2 3 4 5 6 7, directly giving a number. If this is our input and this is the output, then use a sparse categorical cross entropy as a loss matrix. So this will automatically create a sparse matrix for your output. So that's it for today, guys. Now let's meet in the third lecture, and in the third lecture we will see the optimizers. Like optimizers like gradient descent, stochastic gradient descent, mini batch SGD with momentum, ADA grad and RMS prop, and ADAM optimizers. Firstly, we will see like why we don't have to use gradient descent, stochastic gradient descent, and like what is the problems with stochastic and mini batch SGD with momentum and ADA grad, and what is the advantages and disadvantages of each of these problem of optimizers, and what is the advantages of adam optimizers. And like 90 to 95% we are using adam optimizers as a optimizer. Basically this will gives a good accuracy to our model, so that's why we have to use a adam optimizer. We will see it everything in the next lecture. Uh, so for this, basically this is uniform distribution, weight initialization technique, exploding gradient problem, add a grad, add a delta, and RMS prop, exploding weight initialization technique, also be like uniform distribution, Javier, Kimish. We will see it everything, deep out layers, everything. We will see it in CNN also. In the upcoming lectures, we will have a very good like functions. We will see it everything in the upcoming lectures. Thank you guys. Let's meet the next lecture. Jai Hind, Jai Bharat.